Okay, good day. This is assignment number 2 for computer organization and architecture. Let's first take a look at the assignment. It says that given the content of the memory in the figure below, discuss how the entire instructions will be executed by SAP 1 architecture. And for the requirements, um, we've got create a short video showing that you are how the SAP 1 architecture works given the memory content in the figure above. Discuss the flow of the data, active pins, and the behavior of each module. So first is that I have to look for a SAP1 simulator online so that I don't have to create my own. Will save me a lot of time. Thankfully, I found this. It's called sap1-simulator.almedo.io. So as you can see, we can edit the code. So we can uh, implement what's the requirement on the assignment. But before that, we have to convert them into their corresponding binary value. So what we need is this address, location in binary, and 8-bit code. So to do that, I laid the data out here on another spreadsheet sheet, given that these are the OP code for each module. So for LDA, we've got 0000, add 0001, and so on for subtract, output, and halt. So this is column A to C is the assignment. Okay, I started the binary conversion, um, say LDA 11. So the binary equivalent of, or the OP code for LDA is 0000. So that's that. For 11, that's 1011 there. So for add, that's also what I did. So OP code for the add function is 0001, and for 10, that's 1010. That's also what I did for subtract. Get the OP code and the binary for the address, which is 0111. For out and halt, I just copied their OP code and no need to fill out the address bar or the address part because there isn't any address in the instruction. Okay, for the data, it's just the direct equivalent of these decimal numbers to binary. So there, so as you can see, I converted them to their binary with four significant figures. So 0010 for 2 and so forth until we have uh, until 7. Okay, so combining these, we form an 8-bit code. And going back to that simulator, we already have this part. We just have to get them together with the binary of the address, which this. So concatenating what's on B3 and the 8-bit code that we have formed. We have this as the final simulator code, which we can copy and put in that simulator memory editor. So I believe we're good. Okay, if we can actually toggle to readable view. So as you can see, there it is. I think this will be uh, the correct code to fulfill the requirements of the assignment. Okay, so starting off at the T1 cycle. So the T1 cycle is known as the address state. So to describe it, it's just um, getting what's on the program counter to the MAR, which is the scenario here. So from the program counter, it flows to the bus, to the MAR. The active pins are the ones in green. So clock, clear, EP, and LM. So that's for T1. Moving on to T2, that's the increment state. So it's simply incrementing what's on the program counter. So from 000, it became 0001. For T3, uh, it's the memory state. So as you can see, this pathway right here is darkened because the operation took place in this part. The active pins are the ones in green, so it's CE and L1. So what's in the RAM goes to the bus to the input register. So that's that, the memory state. Okay, for T4, it's the execute. We're on the execution cycles. So it's according to the LDA routine, it's simply putting the upper nibble of this, or the higher nibble of what's on the input register to the control unit, and the lower nibble, or the last four numbers, flows to the bus to the more. The active pins are the LM and the E1, or the ticked pins. Also, for in the control unit, you can also see that CLK and CLR have been ticked. All right. Um, moving on to the next cycle. Okay, as what happened here is what's in the RAM flowed into the bus and then flowed into the register. So, okay, take a look at this RAM from T3 and then T4. So it became the data. So this last four digits, or the lower nibble in this RAM is already the data. So see that change from T3 to T4. So this is what we're doing when we are loading what's on 1011 address, which is 70111. Or sorry, that's when we're loading what's on the address 11, which is 0111. So that's that. Okay. This is T4. So again, it's the input register to the bus and to the more, and putting the data to the RAM. So just take note of the highlighted or the darkened pathways. Okay, moving on to the fifth execution, or the T5 execution cycle. So looking at the darkened pathways here. So what happened is that what's on the RAM goes into the bus, then went into the A register. That's the execution T5 cycle for the load module, or the load routine. And for T6, um, no further actions has been made, meaning that there are no operations. By the way, for T5, the active pins are CE and LA, which are in green. Okay. Okay. All right. So now we have moved on to the second routine, which is the add. So this we are adding what's on address 10. So for T1, again, it's memory state or address state, sorry. So what's on the program counter will be put into more through the bus. What's on the program counter will flow into the bus to MAR. Active pins are the same for the load module. And then T2 is also the same for the load module slash routine. Active pins are basically the same. It's incrementing what's on the program counter. And then T3 cycle is also the same. So it's just putting what's on the RAM to the bus, to the input register. T4 looks the same as well. So this is when the higher nibble goes to the control unit and the lower nibble goes to the MAR, goes to the bus to the MAR, and the data has been loaded to the RAM. So as you can see, those are the pathway that has been darkened. Okay. T5 cycle is different for the add routine. So we're putting what's on the RAM to the bus. This is the data. So going back to that, it's adding what's the data on address 10, which is 6. And 6 is 0110. So this is already the data. So as you can see, that's 0110. T5 cycle is putting that data into the B register. So the green ones are the green control pins are the one which are active. That's LB and CE. So these are also their corresponding values. And CLK prime and CLR or the clock and the clear control pins has also been ticked. Okay, and the T6 for addition or for the yes, for the addition routine is putting what's on the B register to the arithmetic logic unit and the A register also to the arithmetic logic unit and adding them together. Okay, so there you go. Yeah, T5 and then T6. And the value in the ALU block will flow through the bus and then back to the A register. So here is the current value in the A register block. Okay, that's for T6 for the addition routine. Okay, next is now we're on the subtraction routine. So the first T cycles are pretty much the same. Uh, for T1, it's just putting what's on the program counter to the bus to the MAR. Active pins are the ones on green. T2 is the simplest step, which is incrementing the program counter. Active pins are the same. So T3 is um, putting what's on RAM to the bus to the input register. So as you can see here, the binary command is 00100111. So that's that. Goes to the bus, then it goes to the input register. T4 is kind of like the same. Okay, the higher nibble goes to the control unit, and the lower nibble goes to the bus to the MAR, and the data is also loaded to the RAM. Okay, and then for the T5 state, what's on the RAM? So as you can see, the CE pin in the RAM and the clock and clear in the program counter is also green. The clock and clear for control unit is also green, and the LB control pin for B register is also green. So what happened for the T5 cycle of subtract, which we're still on subtract by the way, this is just on green, but we're still on the subtract routine. So what is in the RAM? What's on the RAM goes to the bus to the B register. So as you can see, this is already the data and no longer an instruction. It goes to the bus and it was loaded to the B register. And for T6 cycle, uh, it what's on the B register goes to the arithmetic logic unit. What's on the A register goes also to the um, arithmetic logic unit. The SU and EU has been activated. Um, that's to subtract, and it flows to the bus. What's on the A? What was computed in the ALU flowed to the bus back to the A register. So this is our current value for A register. Okay, that's for T6. Now we're on the out routine. So T1 is the same. Program counter goes to the bus, to the MAR, so 0011, 0011. And then T2 is just incrementing the program counter. T3 is getting what's on the RAM to the, or sorry. Okay, so T1, in T1, aside from getting the program counter, what's on the program counter to the bus to the MAR, the instruction has also been reloaded to the RAM. Not sure if I mentioned it on the previous routines, but that's how it is. Um, for T2, simplest step, active pins are on green. So from 0011 or 3, now it's 0100, which is 4. T3 cycle, same. Same pins are active. So what's on the RAM goes to the bus to the input register. And since it's already an output, okay, so it goes T4 state for the output routine. It just goes straight, it just went straight to the output register. So we have this value, which came from, oh sorry, for the output routine, it's simply just putting what's on the A register to the bus to the output register. So what we've computed on the first or on the previous routines, it just went to the bus to the output register. And for T5, no operations. T6, also no operations. So we're moving on to the final instruction, which is the HLT. For T1, it's just program to the bus to the more and putting the instruction to the RAM. For T2, same active pins as before, it's just incrementing the program counter. So from 0100, it's now 0101. And for T3, uh, it's putting what's on the RAM to the input register. So from the RAM, it flowed to the bus to the input register. And for T4, yeah, no more T4. That's about it. That ended the instructions that we have um, put into the memory. So checking the binary value, this one is equivalent to 10, if I'm not mistaken. So checking that, you're loading what's on 11, which is 7, adding what's on 10, which is 6. 7 plus 6 equals 13. Subtracting what's on 7, which is 3. 13 minus 3 equals 10. So I believe the SAP 1 simulator uh, computed correctly. All right, so I think that wraps up my assignment, and I'll submit this via link. And I think that's it. Thank you. Bye bye for now.